Okay, so if we go to the Excel sheet and we have two variables. We have tubing diameter, two primary variables. And to calculate this is the net present value, right? And if the way we moved it yesterday is that if we change either the tubing diameter or the dew point controller temperature, and let's just change that. I'll change it to 150 millimeters and 0 degrees C, okay? If I change those two numbers, then automatically the net present value changes, correct? And it changes through a chain of integrated calculations, going from the reservoir, okay, because at the end of the plateau, you're producing so much gas out of the reservoir. The reservoir at the end of the plateau has a certain reservoir pressure. The rate calculation says that with that pressure and this amount of rate, with that pressure and the minimum tubing pressure, because you have the minimum tubing pressure at the end of plateau, you calculate the well rate at the end of plateau, right? From the rate equation. Average pressure, PC, minimum tubing pressure. You have A and B are given. B's changing with the tubing diameter. So you have A and B. B's modified by the change here. Okay, we have the delta pressure squared. We can solve that equation, the rate equation, for what? What do we solve the rate equation for? For rate. For the well rate. Yeah? At the end of plateau. But we know how much we're selling to the Germans because that's this percentage of the initial gas in place. So we know the total volume being sold per day. And we now know the well rate volume per day, so we can calculate the number of wells. Right? The number of wells affects the cost because each well costs so much money. So that translates into a change in the cost, this tubing diameter. Right? Mainly it's affecting the cost. Because we're getting the same amount of gas, the same amount of revenue, no matter what. It's just taking more wells. So the tubing diameter is a pure cost-based variable. In this case, it's not affecting how much gas we get out, the recovery, or anything else. The temperature of the dew point controller is controlling of the gas that's produced out of the reservoir, how much is sold as a liquid and how much is sold as a gas. The liquid price of the products is 7 to 10 times greater per mole than the gas. So the more we can extract out of the gas stream, producing to the surface as a liquid, the more money we make. So the dew point controller temperature is giving us an added value. The lower the temperature, the more revenue. But it's not only affecting the revenue, it also affects the cost. Because the colder you make it, the more fuel consumption, the more expensive the dew point controller unit. So you're also getting a cost effect. So the dew point controller temperature has both effect on the revenue and the cost. Both. Okay? That's bringing in this optimization problem. Because if you only gained, if you didn't take into account the costs, you'd go to minus 40 degrees C, you'd get more money, right? And that would be the problem. I mean, that's all it would be. It would go straight to minus 40 C. And if there were no cost negatives for the tubing, okay, then you would, of course, go to 400 millimeters or whatever it was, the maximum. But because there's this cost effect there, then so there's this interplay between the tubing diameter and the temperature that affects the net present value. So you can just make, a matrix. You could make a matrix of combinations here, and if you did that and plotted the net present value each time on a plot where we have on the x-axis the diameter of the tubing, and the y-axis we have the temperature of the dew point controller, and we plot the net present value. But I'm plotting the minus of that so that instead of it becoming a maximization problem, it's a minimization. And the reason for that is that it's easier to think of yourself as a marble rolling to the bottom of a hill, or the lowest spot that you can roll to. If my son, he was asking what I was sketching, And I said, well, it's like you do rollerblading, and they've got these ramps, okay? And I said, if you put a marble and you let it roll down, it would find the lowest position. He immediately understood that, okay? And that's what the optimizer is trying to do here, in a sense, is trying to find the lowest spot, or the highest spot, okay? And so the problem we found yesterday was that there were, in the roller skating environment, there was a bowl. They call it a bowl. When they rode down and then they come up again. There was a dual bowl, okay? There was 2 bowls, okay? And in between the bowls, there's kind of a ridge, an edge, you know, because it's low here, it has to come up here. But then around the edge, it's very high. So it's a little bit kind of what we have here, okay? And so the idea is that depending where you start, depending where you drop the marble on the edge, okay, or wherever you start it, it will end up a number of different places. Now, it may or may not end up only at the 2 low spots. You've got a low spot A and a low spot A prime, right? Those are the 2 things we found it ending up at. Okay. Now, why are we doing this? It's not just, why are we doing any of this? I mean, Bjarne was giving us all these equations, which we probably will never really use. Why we're doing it is because we're going to do a project using this integrated model to actually do something for the company to try to figure out what are we going to develop. Okay, we're actually going to be using this. But we have to recognize that when we push the solver button, it's going to give us an answer. And the answer may very well not be the real answer we want to have, or we have to make a decision that these 2 are equally valid optimum. Okay? We have to understand if we're going to do some kind of assessment, we're making negotiations with the Germans about a gas contract, about selling gas from this field. We're actually doing engineering. We have to understand, when we push the solver button, what is it giving us? Can we rely on it? Is it giving us maybe one of multiple solutions, and so forth and so on? So that's why I'm trying to, because we're going to use this project with these 2 main variables and maybe one more to solve a real life problem in the next hour. Okay? And before we do that, if we don't understand a little bit of what the optimizer is doing, you can get in trouble. Basically, that's what's the bottom line. And I want us to avoid getting in trouble. I want us to assess that based on what we saw yesterday. So this is a kind of a map of this bowl. That's what I'm trying to plot. So the idea is that there's a low spot here and a low spot here. Has anybody then looked at this and agree or disagree with this is a map. I don't do orienteering. I don't go in the mountains with a map. I mean, but this is like a map. Now, from what we saw yesterday, does anybody see whether or not this looks correct or not? That's the first question, because maybe I've made a mistake. Does it look correct or not? We found this value and we found this value, right? And this was about 117 millimeters. Yes?
One of the top of the field on the left, it should be minus 40, right? Because one of the highest net present value was minus 40.
That's right. That's
so
there.
Move
Well, but realize that I'm plotting minus net present value. So now it's the bottom. Okay, so this is the low spot. The top of the hill yesterday was a low net present value. So you just have to think upside down. Okay, so this is the maximum from yesterday, but now it's being plotted as a minimum. Okay, so let's just say that we start with this point here. I don't know why. We start with a large diameter and a cold temperature, minus 20. So what should happen is that this is kind of a high, okay? And if you're a marble, then what should happen, if you're a marble, is that you're going to go down, and basically it'll go kind of along here, because nature's working on gravity. It's not doing iterations and derivatives and stuff. It just automatically finds the minimum. It'll go through here, and it'll actually intersect this contour here perpendicular to that, right? Why would it be perpendicular to that? That's right. Okay? So it keeps going like this, and it goes down like that. And again, it crosses here, kind of orthogonal, and maybe it's got a little bit of shape, and it comes in like that. That's how the marble is going to go. And of course, it'll, hit the wall. And then it'll start doing stuff you don't want to deal with. Okay? The marble. So that's what the marble does here. And if we start with the marble here, it'll do the same kind of thing. It'll kind of move along here, perpendicular, here, like that. Okay? This I can understand. I don't understand any of the mathematics of what Bjarne gave us the other day. I still don't understand them. Okay? This I understand. This is all you need to understand. Okay? To use optimization. But if you don't understand this, then you're going to get in real trouble because you're going to push the button, you're going to get a solution, you're going to not, you're not going to be thinking. So now let's think about what might happen. I don't know if it would happen mathematically, but if you put a marble at the top of the hill here, okay, what's going to happen, Alex, if you start here and you roll the marble down?
Well, are you thinking in real life or what else?
In real life, if I just have a marble.
Well, if you place it exactly the same, then it would kind of roll down to the center, I guess.
It would roll down here, and the way I've drawn it is that it's going to hit perpendicular here, it's going to hit perpendicular here, and then it gets to the bottom right there. Forget about momentum that it goes up and down like that, okay? It gets to the bottom, and as soon as it hits a minimum, okay, then it's got a direction in this way, and along that direction that it's moving, it is at the minimum, right? Along the direction it's moving. Now, what will happen is that means that there's a minimum here. Because if it goes further along this direction, it'll go up. And if it goes back, it'll go up. So along the direction of movement, it's reached a minimum. Yeah, Robert? Yeah, that's, let's see here. Yeah, bigger cursor. Does that help? A little bit? Not really. Problem is if I'm going to draw, is that, maybe there's a...
From 95 to 110.
Is that a little better? Okay, yeah. Or you can move up here. Okay? So we're moving along here, and along the direction of movement, it is at a minimum. Okay? Now, that means that there's another possible solution right here. Okay? Not for the optimizer, but for the marble. Okay? Because the marble has a direction, and unless I blow, if you've got a fan over here and it's hot at the Tinikastalm where they have these things, they've got a fan that blows. So if you've got blowing movement, that marble sees a little bit of push in the direction towards A. That's all it needs. It perturbs towards that, and what it'll do is that it'll go there, it'll get a little push, and then it'll move down to this one here. Okay? And the optimizer is, in a sense, doing that because it's looking in both directions for change, to reduce. Okay? Now, the question is, will the optimizer move it in this direction? Which direction it will go? Okay? And which direction would that go, Alex?
Depends on the optimizer.
Okay? But
Normally it would go where the which side it is.
okay. And to decide which side it would go from this point here, it's going to have to take a derivative, right? That's what Bjarne would say. We would take a derivative. If we take a derivative at that point, what's the derivative? In the direction of, in this direction here along the dashed line. What is the derivative? It's 0. So how's it going to know which direction to go?
Well, that's the second derivative.
Okay, and which direction does it go then?
That's
But it can go, if you call that, it can go that way or it can go that way. So it has to calculate a numerical derivative, right? It has to calculate a numerical derivative because there is no analytical derivative here. So it calculates a numerical derivative. So which direction will it go? Will it go this way or will it go that way? That's the question. What do we think? Well, let's say it's very accurate.
If you take the second derivative and then second derivative minus the function, at that point.
I mean, it's on a flat surface. With respect to that direction, the derivative at that point is truly 0. If you had an analytical derivative, it would be 0 there. It wouldn't know which direction to go.
But the numerical derivative.
The numerical derivative does say something, yeah?
So maybe it would change like the delta, the PPC, the viewpoint controller, but tiny little bit in either direction, and then
To get the derivative, you have to do a perturbation on delta t. I want you to go there, Alex. I want you to take us which direction it's going to go.
Well, that's completely dependent on the optimizer you select.
Okay, so
You can have, most likely it will take one perturbation in one direction.
which
Then-
direction?
That depends on the optimizer. Some optimizers take perturbations in the negative direction and some take in positive direction.
Exactly. So it's not the method of solving, it's which direction you take the derivative in. Do you take you're at a point there, and you take minus delta t or plus delta t. Okay? All of the other algorithm of the solver could be identical, absolutely identical. Solving the Jacobian, could be Aaron and Curtis writing exactly, that's a bad analogy, okay? It could be Curtis on Monday and Curtis on Tuesday, okay? And if you write plus the delta, the perturbation, which way is the wind blowing, will decide which one it goes to, okay? Bjarne didn't talk about that because he talked about, in a sense, knowing analytical derivatives. Here, we're at the mercy of this is a case where we're at the mercy of, does it really matter, a plus or minus derivative?
And of course, some optimizers will take perturbations in both directions and decide where you're going to.
Okay, so this becomes a little detail, a small little detail, will move us, in a sense, even for this case where, in reality, if you took the analytical derivatives, you really wouldn't know where to go, right? Because if you had the analytical derivatives exactly at that point, you wouldn't know where to go. Is that correct? If you took analytical derivatives, you wouldn't know where to go. You would stay there because this is a saddle point.
Well, a lot of optimizers will take second derivatives and figure out that they're actually not that reactive.
But unless you leave that point, you don't know. I mean,
Well, if you take the second derivative.
yeah. Then you know that you're at a high. You're not at a low here. Yeah, that's right. Okay. That's true. So basically, what's going to happen is that you're going to roll down to the middle point, and then it's a bit arbitrary. Is my point. It's a bit arbitrary whether you roll the one direction or the next. Okay. It's kind of which way the wind's blowing. Okay. And of course. So you've got all sorts of possibilities to, I suppose even the one, though it's theoretical, for a numerical case, you would either go up or down. You wouldn't get stuck here. But actually, this is what we call a saddle point. Okay? It's a minimum only in one of the variable directions. Okay? So now we don't know, for example, if that's the case, the shape of the net present value along this optimal tubing diameter, because there's clearly maybe one maximum here, but there could be more than one maximum along that. So there could be, if we draw this surface, if we draw the net present value along AA prime, there is a chance that we'll do this. Minus net present value, and this is from minus 40 to plus 80, and this is minus here, so we've got the minimum here, and what we saw yesterday was that, I don't know, maybe it was a little bit better at minus 40 than plus, more or less the same net present value. And then what we're saying is that we suspect there's some saddle point here. Now, it might look like this. Okay. It might look like that. This point being this point here. But it could also be looking like this. Okay? It's not a very, very pretty picture, but okay? So there's now the possibility that it gets here, Alex takes the second derivative and says that we're looking for a minimum, it's at a maximum, so you push it one direction or the other, okay? Which direction he goes, I don't know. Let's say we go left, okay? Because it's Tuesday. We go left and it finds this right there. That's what we call a local optimal, okay? It's looking either for this one or for this one. Basically, you have two kind of global. If these net present values are the same here and here, which they're close, these are kind of the global for our problem. But now we've got a couple of local minima, okay? And if you've got it along one traverse for diameter of 2 being equal to 117, then you might have more local minima in this whole area here. There might be a whole area here with local minimum. Okay? So you start seeing that for what's really a simple 2 problem, simple models, actually analytical models, you're calculating everything with an equation exactly, then you end up getting what's looking like it might be a fairly complex surface in 2 dimensions. Okay? So this is a little bit of the practicality of optimization, and the solver, if you have this kind of surface, what you really want to get to is either one of these, maybe both of these, right? How do you get there? Okay? So there's, this is a whole field of optimization, but our little problem here, what I'm trying to do is illustrate that there's a lot of complexity to that, and you'd like to know a little bit about that before you start using this integrated model with optimization. Okay? Because so what's the recommended strategy given that this may have local maximum net present values? It might have 2 global. I'm saying 2 global, meaning that these are basically equivalent options, dramatically different from an operational point of view, but they have essentially the same value. Okay? So you might have multiple global optimal, if you want to allow me to call it that. So you got local, possibly local maxima, and maybe more than one global. So what's the strategy? We have to come up with a strategy. We can just not use the program. What kind of strategy should we use? Shinazana?
have local and from trade issues.
What she's saying, if I understand right, is that you start with 20 initial estimates. Resolve the problem 20 times, the optimization 20 times, starting from 20 different initial sets of estimates. Okay? That makes sense to me as far as computationally. And then what do you look for once you've done that?
And then we are looking the bottom rate to see if we have several minimum or maximum.
Okay. So let's say we're talking net present value again. So we're looking at maximum. Okay. What I suspect is going to happen if we do this, okay, and we can do this, I mean, I can ask you guys to do this, and that's what I expect you, unless somebody else has a better suggestion, okay, that you do this. Every time we solve a problem now, we have to start with several initial sets of values. What I suspect will happen is that all of the optimizations you run will fall into one of two categories. It'll find either A or A prime solution, okay? It'll generally fall into one of those two maximum. And for this particular problem, if we've done it right, although Robert, you said I had maybe an error in my spreadsheet, so we have to make sure that in yours, okay, all right. Well, I probably have one we haven't found yet. But the deal is that we've got, for this particular problem set of assumptions, we have two almost equally good options. Okay? Now, this is an engineering group. What are we going to do? Which option do we want to take? Anybody have a feeling for which one you think is the better option?
Maybe we have to look at our criteria and ITV.
Right.
Look at what's easiest for which company best for the case.
Yeah. Bring in other, it could be soft, like risk, okay? They could be soft criteria, is what you're saying. Or it could be, I think somebody mentioned yesterday, use rate of return, use other economic factors. So we need to bring in other issues. Now, you could try to bring those in to the objective function itself, right? That would be one option, that you quantify it. So actually that it will change the shape of the surface so that one of the two maximum that are equal today with the definition of our net present value as the only objective would be shifted to take into that, you change the whole surface. So you look for a new maximum on a new surface. How might we do that if we bring in, I mean, can you think of a way to do that here? Or we can just do it soft. We simply say that, we within $500 million, we call that equally good solution. We're finding two solutions, two optimal. Okay, and you just carry that forward, and you send that to management, and you let them decide. Well, this involves a big investment of a dew point controller system. That's an initial investment. If you don't want to do the initial investment, then you can just do it the other way and forget it. But then someone comes along and says, well, that's true. You don't have to have that initial investment. You don't have to go to Chase and borrow the money for the dew point controller. But in 10 years, this could become the hub of a new processing facility that not only this field comes into, but that you provide, there's some other satellites around. They're not going to be able to afford to put in a dew point controller on their system because it's not big enough field. But we can take their gas, we can buy their 10 mole% of gas, convert it to liquid, make more money off of it. Okay? We'll buy their gas, strip out what we can make more money on, so it can become a potential money maker into the future. You see what I'm saying? Or not? You take, this is our big field, because this is a pretty big field. I don't know if anybody calculated the volume of this, but it's a pretty big field, okay, the way we have it now. So let's say, and generally where there's a big field, there's probably some fields like this around it. That's the way God works. Okay? So this big field can, within its budget, add a dew point controller system. But none of these others could. Okay? So you've got a gas export line, and what we could offer these fields here is that they could pay us, we put in the pipeline, and they can pay us for coming into here, directly into the pipeline, or maybe they have to go into here for some processing on our process facility, okay, because it's, knocking out the water and so forth. That's probably what would happen. They would come in here. They wouldn't go directly into the pipeline. That would be an option they would have to consider. But they come in here. Once we're getting their gas in, taking the water out, dewatering their gas, preparing it for export, if we put their gas through our dew point controller, we can take some of the value of that. We give them the value they would get selling it as a gas. Okay? That's all they have the right to. But then we take and we extract out the liquids, okay, and we get extra value from their gas. But that might not happen for 10 years. Mike, do you want to make a comment?
Yeah, I just want to make a comment. We talked about PDO in the class 2 weeks ago, and one of the things that now all companies would like to put in the PDO is how the infrastructure that they put is going to be used in the future by others. So that's something that they have to do. Secondly, you'll find out that each one of these mature fields in Norway have now a new group which is called business development. And one of the things that these people are looking is how to use infrastructure in declining fields to sell services to other people. And the third thing, that's something that you have to realize, the cost, they call it tariff. The tariff that all kind of users have to pay to the main platform that take the oil or the gas and process it is very, very high, particularly in the North Sea. Tend to be with some of the old fields, let's say like Gulfax A. In fact, they don't live anymore the oil production. They live for taking gas and processing it for other people. Even Ecofis, who still have a lot of production, Valor has to sell their gas via Ecofis because they don't have export facilities. So, in fact, most of the new developments now in the North Sea are based on the fact that someone else had the facilities, but the one with the facilities make a lot of money. But that's not only in the North Sea, it's also in Oklahoma. Someone that are lucky to have a pipeline in some area, and then everyone is knocking on his door. Hey, can we use your pipeline to transport our gas, or you buy our gas? So what Curtis is bringing here, it's a very important issue for management in the North Sea and make the economy of many new fields viable, but also a lot of the old fields, they live exactly, and they never calculated for it. There are zero value in the book. It's already been depreciated, as we call it in the North Sea. Yes, Odom.
Just a question that these tariffs, are they regulated?
No, they are not regulated. And in fact, they say that if the government will step in and start to regulate the tariff, suddenly a lot of small fields in the North Sea will become economical. But if you're a company like Exxon, it's interesting because the main platform might be a consortium of Exxon and Statoil. Okay? And the company that sells it's a Nosh Hydro, Statoil Nosh Hydro. And the consortium of Exxon and Statoil charge a lot of money. The consortium of Total and Statoil, in fact, it's the same operator, but it's a different ownership. So it's a big game in the North Sea. and fortunately for a lot of companies, in fact, Statoil, all the mature fields are based, if you look to Statfjord, these fields already have to go to pension for a long time ago, but then they find out that they can use them to process other people. The value in the book is zero because there is in Norway, the government gives kind of a tax, kind of a bonus to everyone that invests in something, and they call it depreciation, which is basically kind of a tax bonus that allows you to write off the investment over a short period of time. So people have, the energy to put that, even if maybe the economy is not very clear. But then God made it such that they make big money on it. So it's a big game, and it's a very interesting observation.
Yeah. So I think for this case, what we'd like to do, if you add any potential Q gas extra, okay, coming through this dew point controller, okay, it's somebody else's gas, and it starts coming in at some time we don't know in the future. But of this gas, what we can do is that we can take out NGLs. Okay? We basically buy their gas from them, pay them what they want. Then we extract 10% of that gas, turn it into a lot more value. Okay? So we're making money off of their gas, more than they could make. Now, if you add this, which you can formulate in our spreadsheet through decline curve analysis, you just put in volumes. You just add volumes at some time in the future. You basically have the time factor, which will be affected by the discounting. Of course, this is a big uncertainties. That's a big uncertainty. But bottom line, what you know is that if you start doing that, you'll add late revenues that will be very attractive. Now, it may not affect the net present value dramatically, but probably it'll be enough added net present value that it'll show up in our analysis, okay? And that the surface that we've been looking at before will change, okay? That this will become the true low spot, or the high net present value. It'll change that whole surface. It'll rotate it, in a sense, downward, okay? And then you may still find two local optimum, okay, when you do depending where you start. But the difference between those net present values will probably start getting larger and larger, okay? So it's a kind of deal where there's no guarantee it's going to come, okay? This may all be zero. But buying a dew point controller and so forth, that's a very low risk item, okay? And maybe borrowing the money to buy it today is harder, and it's more expensive. But there's very little risk associated with acquiring that additional processing capacity. We're going to look at a problem after lunch of gas cycling. Alex is going to show it. And there we end up with basically, should we do gas cycling, defer gas sales, make more oil out, or not? Okay? And if you start discounting and adding economics, you find out that it don't really matter. There's not a lot better net present value if you do nothing versus if you buy all of this infrastructure to do gas cycling. That's a different problem, because even though you might have the same net present value for do nothing and do gas cycling, the problem is there's a high risk associated with it. There's a lot of infrastructure if that you happen to inject gas and it just shoots through to the producer and you get no added value of recovery through a geologic unit you didn't include in your reservoir model, then it's a higher risk factor. So that's a case, we'll talk about it this afternoon, where the risk issue may become a factor. Okay, but in buying a dew point controller, I don't think, Mike, there's much risk involved in it. So that this potential upside probably would weigh towards buying the dew point controller unit, installing it, and using it.
Curtis, you're kind of reflecting it with 4 years ago, was it, that we both invited by Roskilde to give a course in Oslo on business opportunities for all fields in the North Sea. We kind of scratch our head very much, and they say, oh, you come and say something. The basically the thing in terms of you are a farmer and you have this old cow the meat is better. So it's what we do. So, Curtis came with some example in Oklahoma, and, I came with something. When we came to give the course, or to give the talk, there have been 50 lawyers and economists sitting in front, and they want to hear, all this wisdom from these two guys, how you get some value to this old cow. But I think if we had this exercise that we have now, and we thought about that issue and show the importance of the tariff and the investment in infrastructure, and probably we can talk to them 3-4 days without any effort. We also have learned something in the last 4 years, but really that is now the game of all the mature fields in the North Sea. What Curtis is showing.
Yeah. Okay. So anyway, that's kind of an aside. But basically, there's no difference between this and going into the mountains of Norway without a map and a compass. Okay, you're stupid, and I would never do it. Or you're a mountain man and you like the thrill of maybe dying or not. Okay, if you go in without a map, understanding. And today you go into the internet and you get the GPS coordinates of where you have no cell phone. So if you want to stay safe, you only travel through the mountains where you have cell phone connectivity. Okay, it's not that different what you're doing here. Alex, when you go off-piste, right? Okay, he probably doesn't do a lot. Lives a little bit dangerously, but at least you check the weather report if there's danger for this part of the mountain for snow. Okay, it's orientation that you're obliged to do. A little bit of orientation. Now you can't make the plot, and if you got 5 variables, it's impossible to graphically show it. But if you have 5 variables, you can always do what I call line diagrams. Okay, you can say you fix all the other 4 variables and you change 1, and you start getting a feeling for the terrain of the objective function, and it's worth the extra effort to do it. And you can do it, you just have to make the tables like we did manually. If you push the button and run solver, you're just asking for trouble. Okay?
So basically what you said is no automation in that optimization. You have to change the frame and try to find out what.
Yeah, or you can hire Bjarne as a consultant, and he can take the output from the solver, all these derivatives and things like that, and maybe he can help tell you about, is it global minimum, is it not, and so forth and so on. But the strategy that Snezana suggested, which is kind of I call it the Oklahoma strategy, you try 4 or 5 sets of initial values, and if you keep getting to the same solution, well, you feel comfort and you say, okay, that's good enough. Okay, if you're a little bit paranoid, you try 50 initial solutions, and if you always get to the same solution, then you feel good and you go home. And if you live dangerously, you put the one initial solution, you go and you take it and you go home. All right? But that's not good engineering. So when you guys are going to do this exercise now, you have to think about this. Okay? And now the exercise. This is taking the problem. And this is going to be the class project that we work on basically until lunch. Okay. We're going to take the starting point from yesterday, and we're going to say the following. The Germans tell us the following. We can buy all the gas you can sell us. Okay? That's today's situation. Everybody needs as much gas as they can get. They don't like the Russians. Okay? They don't like this, the Russian Putin is, he's going to retire in a few years, and what he's going to do, he's going to be the head of Gazprom. Just wait and see. Okay? So they don't like that power thing. So they want as much gas from the friendly Norwegians as possible. But they're not willing to risk buying more than half of what you say you have. Okay? So whatever you think you have, we'll buy half of that in some period of contract we can negotiate between 8 and 12 years. Okay? That's basically our mandate. Okay? Is that clear? So they're willing to buy half of the gas. Now realize that we, the operators, and we have this field, we're not quite sure how much gas we have. We maybe know plus minus 50%. You know, the geologist, depends how good they are in the seismic and so forth and so on. We have an uncertainty. If we're willing to risk, we might take the upper estimate of gas in place and sell it to the Germans for 50%. And we end up short, if we end up short and our gas in place wasn't what we thought it was, we're in deep trouble. Because the Germans, when they write the contract, say that if you don't deliver that amount for whatever we agree on, 10 years, then you're going to be our slave. You're going to be paying us. Okay? These contracts are terrible if you can't sell the gas that you promise. Okay? So, we're the company. We've got a large field. Do we have basically yesterday's gas in place? What was the gas in place yesterday? That was our starting, the current gas in place. 410 to the 11th cubic meters. That's how much gas in TCF? I think in TCF I can't multiply by 35 and divide by 10 to the 12th. About 14 TCF. 14 TCF. That's what I'm giving you. The first big gas field in Norway was Frigg. It was about 7 TCF. Ormen Lange, I think around 10. Yeah, I think around 10 TCF. Troll, the biggest in Norway, 45 TCF. Okay? So this is a big field. But if we say that we have uncertainty, it could be as little as 50% less than that or 50% more. That's our range of gas in place. So it's a big field. But if you go down 50%, then that's only, what, 7 TCF. That's a Frigg-like field. If you go up 50%, that's 21 TCF. That's half of Troll. Okay, so we're talking really a big field, but it's like there's a lot of uncertainty. We only have one exploration well or something. Because we only have one exploration well, we only have one permeability thickness. Okay, so we're going to say that the permeability thickness is another thing that can vary in a field, and we're going to say that it can vary a factor of 2. 2 higher, 2 lower. Our current assessment is 500 millidarcies. It might be a Darcy on average. It might be 250 millidarcies. Okay, that will affect the A constant. Okay, so what we're going to do, we're going to have a group here, the left group. I'm sorry, yeah. You're the right group on the wall. Okay, you're going to take our base case, but since we've already, so we'll keep that. I'm trying to think whether we should change. Let's change that because I don't want you to take advantage of already us having solved it. So let's say that our G star was, what was it now? 4, 10 to the 11th. Is that what it is now? Okay, so let's make this 3, 10 to the 11th. Okay? And the A star can be we've got I think this is okay. 1 to this is okay. That's what it is now. Okay. Now, each of the groups, you can work in twos, or if you want to turn around and Steiner can consult up or down or whatever. You can work in groups of 2 or 3. Moving to another room is an alternative where everybody we
can go to one of the. We can go to some of these working room. 4 or 5.
But those are downstairs, right?
Downstairs.
Okay. Because that way the whole group it's 2, 4, 5. It's not too many, but I mean if you want to. The point is that you have a working group. But each one of you want to be doing it, and then you want to be talking about the results, because you're going to make mistakes, or you're going to do, okay?
There's no projectors in the
Well, we have to come back. I thought, after lunch, then we'll come back and we'll look at the results. Now, yes. Okay, I haven't told you about that yet. Okay. It's not an input, but it's telling you something. Okay. So what we want to do is we want to look and make this assessment. And what you're supposed to come back with is a recommended optimal field strategy. Okay? That's what you get. So it'll tell how long do you want to sell to the Germans, what tubing size, what's the net present value, all the key results. You come back with the development strategy. Okay? And then we're going to compare these development strategies, because you may put the case with 50% more gas in place, but a lower permeability, and you may find that net present value might actually be less than, a lower volume with a higher kH. I don't know. We'll make that assessment. Okay? If we come back and all of the groups have the same tubing size, okay, that's an important conclusion. We take that out of the assessment. We now know what tubing we're going to use. So we're going to look at kind of all the key results from each group and try to make an assessment. VR, what this is meaning. This is what I call voidage ratio. I don't think anybody else calls it anything, but Mike Vetkovich introduced the concept for gas reservoirs. It's basically how the capacity to it's like the PI. It's like the productivity. It's how fast you can take gas out of a field divided by the volume. Okay? Basically. So it's kind of like the QG field max, if you will, the potential, the ability to take out of gas, divided by the gas in place. Okay? So it's voidage ratio, no, not voidage ratio, drainage ratio. That's yeah, voidage. You're voiding the reservoir. Okay, voidage ratio. Now, the bigger that number, the faster you can empty the reservoir, right? The smaller the number, the longer it takes, in a sense, on a relative, everything else being the same. So what you kind of have is that you have for this low gas, high perm. No, it must be reflecting. Let's see here. Let's see, high. Yeah, because this is, I think, equal to G times A. No, I've got it upside down here. Yeah, this is it actually should be. Yeah, so it should be. So these should actually be reversed here. This is basically 3 1/3. Yeah. So the higher the number, the faster you can empty the reservoir. It's a way to think about it. Okay. So this is a lower voidage ratio, a higher voidage ratio, and it's I've selected it such that we have a range of about 10. Okay. By the way, this term here, Vetkovich showed, is the one constant in the ARPS equation from 1942. It's basically the percentage decline per year. You go to a bank, they'll say, well, what's the decline rate? Okay, what's the decline rate of your field or your well? 10%. Saudi Aramco, they say, well, we have a 2%, per year decline rate. Okay, and in Norway, it's very high. It's like 12, 15%. It's very fast. High permeability, you can empty the reservoirs very fast if you want to. So it's effectively, they called this D in the ARPS equation. That's effectively what it is. Okay? All right. Now, this is very important. I don't know how much checking we did yesterday, but we all kind of got the same answers, and we want to make sure that before we start this exercise that we're all at the same starting point for everything else. Okay? And that we have all included, for example, the fuel consumption, we brought that in as a factor. That was important. Are there any other issues that we're not addressing in this integrated project that we should be? Does anybody feel discomfort with? We've got main cost items, main revenue items. Any questions about what we have as a starting model? And we want to make sure that the starting model is the same for all three groups, except for these two numbers. Otherwise, you'll be comparing apples and watermelons and mangoes or something. Okay? We want to compare apples with apples. Everything except these two parameters should be the same.
But the voidage ratio, is that entering in the calculation?
No, it's just an orientation.
Orientation, because the A, in fact, okay.
Yeah, it's just, for me it was an orientation. It's how I selected, the uncertainties of plus minus 50% on gas in place. And, with one well, that's probably realistic. There's probably a larger uncertainty in average permeability after one well, but if the first permeability you get is relatively high, I said 500 millidarcies. A nice clean section of a sand because we're assuming a tank. Probably, if I've got a nice thick section of 500 millidarcy sand, the next well is not going to have 5 millidarcies, or probably not even 50. Okay? It might have a darcy, it might have 250, but it's not. If you drill in and the first well you drill has 5 millidarcies, then the next well might have a half a millidarcy. Because clearly there's a dirty sand, there's more shale. Okay. So the higher the permeability of your exploration well, the more likely you have a relatively homogeneous, less heterogeneity of permeability. That's anybody know this soccer player? Okay. Could be the next Ronaldo, and I just said, no, thank you, being your friend. I could become his agent or something, I don't know.
So, Candice, we break now here, we go to the cellar.
Yeah, but I think what we want to do is we want to make sure we're on the same page with all the same numbers first. I want to do that double check together. So this I want to do together.
The fuel consumption that we had,
Yeah.
probably this one will be different for each one.
We want to use the same model.
Yes, but why don't we check that part? Because
Yeah.
that part was changed, and probably
Yeah.
people have
Yeah.
different solutions, and then we
Okay.
have one logo for everyone.
Right.
The new spreadsheet, if is corrected, it's learning, by the way.
Yeah, that's probably the safest, is that we all go, if everybody starts with that off of its learning, that's probably the safest, because then we all start with the same bug that I have in there. It's the same mistake. But I thought I'd go through that just to double check, because even yesterday when I put in the fuel consumption, I didn't feel complete comfort with what I did. So We want to take the time to do this double check, this double. Okay. So this is what I posted essentially on the It's Learning. We've got the A, the B. Now we're going to change this default, but we'll leave it with the 4. We'll leave it with the default. One of the challenges of this problem description for you is that right now, with this case, it's doing 48% recovery at the end of plateau. Okay? The Germans are willing to accept up to 50%. So if you want to push it up to the 50%, then you have to basically say, well, the plateau period is now variable, can go from 8 to 12 years. And the percentage per year will not be input, but it'll be calculated, right? 50% divided by whatever the time is. So you have to change that a little bit. Then you can add the time variable or the plateau period as a time variable. The other thing is on the economics, we're giving no value for the last 50% or after plateau, which we leave that alone. But if you look at the formula for this revenue, which is, it's kind of an important thing, I'm not completely comfortable with what I put there, because what I say is that if the time of this year is less than or equal to the plateau period, yeah, then basically I provide the sum of these two, which is total revenues through the plateau, divided by the number of years of plateau. Okay, kind of divide up the total revenue into annual pieces. But if you have a plateau time of 10.5 years, I don't think this is right, the way I've set it up, because I'm using a fixed set of integer year values here. So we're kind of trimming off, if it's a 10.99 plateau period, where really the way this is being done, I think it's throwing away that last year, 0.99 years of revenue. And it also becomes non-differentiable, the time. So I just warn you. The way it should be done is that if it's 8.9 years plateau, then this number here should probably change to 8.9, and then it'll be added. Okay, so at least the way it is now. If I go into the let's see, the input of time, if I make that 8.9 years like that, you see, it only gives me 8 years of revenue. And that means that the time variable, the plateau length, is not differentiable. At every year, we don't want that, I think. So we have to change. I don't know exactly if there's a suggestion how to do that, but
as TP is different, it's changing in the organization. This how it can change, right?
yeah, I haven't thought through how to do it, but I just know that the way it's done now, it's not good. That's kind of your challenge. I don't know, but the way it should read is that this 8 or the 9 here should not be 0. That should change to the period here itself. Okay, But then also the dividing up should be handled. So there's some logic that you need to add to the spreadsheet. Okay, and I'll let you guys in each group try to figure that out. I'm just warning you that it's not done properly now. Okay, so that's. That was the one thing that I thought about. I think these are okay. And yeah, so the one thing I wanted to check was on the fuel. So the gas. See, where did we put that in?
The revenue from the gas.
Maybe that's where. Yeah. Okay. So we put it into the revenue of gas. So you want to check this formula. Using the dry gas volume. Now the point one here. The point one here. I have to look. That was related to what?
You're saying maximum you take 10% of the sales gas you got.
Yeah, and that 10% is actually a number in the spreadsheet, right? Because if we happen to change the gas composition and we said we could actually get 15% out of that gas NGL, then that number would be wrong, I think. I think the... let's see, it's... yeah, this is it here. Let's see, point one. Gas sales. Why did I put point one in here? Oh, that was just a number that said that it would take up to maximum of 10% fuel of gas to, yeah. That's probably not a good, because if your gas plateaus are very different, then the fuel consumption. No, I guess that would that would be. It should be proportional to the amount being. Okay. Yeah. All right. So then, yeah. You might make that point one as an input parameter so that you could change that, because the point one is a Curtis factor that we don't know is. So I'd feel more comfortable if, for example, in the in here we say this is the fuel consumption factor. Okay, factor fuel or something, and put point one, and then we go into this and replace that point one with that number there. Okay, that's just kind of to make it a little more okay. That's a change I'd recommend you make. And then again, I don't know exactly how to fix this part, So you just have to figure out something. It looks like you guys are losing people by the minute, okay? Which I'm not sure what that means. That's a bad sign. I mean, why do reservoir simulation when you can do this? Okay. So that the group of 3 is okay, but if you want to join, somebody else can join here, maybe. And make it a little more even groups of 4. So you can recruit one of the centrist. Okay, so you've recruited Muhammad.
Yeah.
You're now a rightist. Iran, well, you got. Are you from Iran? Not yet. Just wait. Just wait. Come back. Your beard's going to be a little darker. Okay. All right. So then, is it more or less clear? I think the mandate. And that way we actually. Yeah. Okay.
So what is the schedule now?
So now they basically can work until we say we come back 1 o'clock.
Yeah, lunch and then after lunch.
Yeah.
Are we going to check the models right now? And integrate the models?
You know, because I think if everybody starts with what I had, then that's what we looked at here. But you have to realize that you're going to make the following changes. You're going to have to go to the first sheet and put in a different gas in place. Yeah. You're going to have to change A. You should probably, for consistency, add this, but you know that's not going to change the result. And I think everybody should be getting the same result then. So if you start with my sheet, if you start with your own sheet, you have to do the comparison between your sheet and my sheet. If you want to do that, that's fine. Just download it from the It's Learning. Yeah?
You said that the plateau can be that variable, but the coverage factor to produce a real is fixed.
Yeah, that's the other thing you have to change here. Is instead of inputting this recovery factor per year, you're saying that this is a variable. The plateau period is a variable. The Germans are willing to go anywhere from 8 to 12 years. But they're not going to buy any more than 50% of what you say you have. Can prove that you have or you think you have. We only have 1 well today. They may demand 3 wells or 4 wells before they sign the contract because they're not willing to take that risk, even though they can hang you out. They want the gas. So basically, you're going to calculate this number here as 0.5, I think, divided by this. Something like that. You have to change the spreadsheet.
So the rate of the field is variable.
Yeah. Because they'll buy as much as we have.
Okay. That's kind of a purchasing strategy that has to do. Probably they have storage, downhole storage someplace, and they want to.
No, I mean the Germans they can use as much gas as they can get a hold of. You know, up to, I mean that's the basic concept here is that you have kind of an open market. Alrighty, so then